Just as there's a relationship between the kinetic energy of rotation and the linear kinetic energy, we also have Newton's second law in terms of rotation. Recall that Newton's second law says that force is equal to mass times acceleration. We also know that for a perpendicular force, so the sine of theta would be 1, because theta would be 90, that the torque is equal to R times F. And we could also replace that by MAR, replacing the force with the mass times the acceleration. We also know that the tangential acceleration is equal to alpha R. Now we can have the torque is equal to m alpha r squared. A little bit of rearranging, you get alpha times m r squared. Recall that this mr squared term is the rotational inertia I. So finally what we have is that the torque is equal to the rotational inertia times alpha. So this is very similar to what we have for force is equal to mass times acceleration. If you think of torque as being analogous to force, then we have the mass term in F equals ma standing in for the inertia of the object. Now that's replaced by the rotational inertia I. And since we're dealing with rotations, instead of dealing with A, we're dealing with the angular acceleration alpha. In this example, we have a box of mass little m, 1.2 kilograms, hanging off of a pulley, except this pulley actually has a mass. Up until now, every pulley that we've used in class has been massless and frictionless, so we don't have to worry about the rotation of the pulley. In this case, we do. The pulley has mass big M, 2.5 kilograms, and a radius of 20 centimeters. So M is going to start to move down, the box is going to start to move down, so it's going to gain kinetic energy, but then the pulley is also going to rotate, so it's going to gain kinetic energy as well. So the way we're going to analyze this problem is by using Newton's second law, and then I'm going to analyze it using energy conservation. For the hanging mass, we assume that the hanging mass is going to fall, as given by the free body diagram on the left, so the tension up minus mg down is equal to minus the mass times the acceleration. Again, assuming that the box is going to go down. Recall that alpha is equal to the tangential acceleration over r. We're going to use that here in a second. We'll make that big R just to make sure there's no confusion. Now the torque on the pulley is going to be equal to the radius of the pulley, r, multiplied by the force applied. The force is going to be at an angle of 90 degrees, so again the sine of 90 is 1. But notice in our second picture there with the pulley that the force being applied is the tension in the string. The tension in the string is what's giving us our rotation. So that's one equation for the torque, but we also have that the torque is equal to the rotational inertia multiplied by alpha. The rotational inertia times alpha. For a thin disk, the rotational inertia, if you look up on page 255 in your textbook, is 1/2 mr squared, and now we're still multiplying that by alpha. I've now replaced alpha by the tangential acceleration over r, so I have, for my torque equation, r times the tension is equal to 1/2 mr squared times a over r. Now I can simplify quite a bit, and I get that the tension is equal to 1/2 the big mass, that's the mass of the pulley, multiplied by the tangential acceleration a. I can now plug that into the equation that I had before for the hanging mass, and now I'm going to plug that in. We have 1/2 big M a minus mg is equal to ma. And now finally I'm going to get an equation of 1/2 m plus m times a is equal to mg. Subbing in all of my variables, I can get that the acceleration is equal to 4.8 meters per second squared. Okay? So we did a relationship between the torque and the force applied in the tension, and we were able to substitute in all of our variables and get an acceleration of 4.8 meters per second squared. In the next chapter, we'll analyze this type of problem using energy conservation. And what we'll be able to do, just to give you guys a little bit of a preview, is to start out with the potential energy of the hanging mass as just mgh. And then that's going to go into the kinetic energy of the box, so kinetic energy 1 for the box, plus the kinetic energy of the pulley. Remember, the pulley is going to rotate, so it has some level of kinetic energy. So what you end up getting is mgh is equal to 1/2 mv squared, that's m for the little box, plus 1/2 I omega squared. This is probably the most useful technique for dealing with rotational kinematics because it allows us to use energy conservation, which is something that you guys should know inside and out by now. Okay? Not actually going to substitute any numbers in here, but this is the level of thinking you have to start going through. We have potential energy of the hanging mass. That's what's going to drive the energy for our system. And then the hanging mass is going to start to fall, and then we also have the rotation of the pulley. So we have to account for both kinetic energies.